So next homework, I think it's like, it's homework 7. Due by start of class Wednesday. Great question. Any other questions?
Will the material from that homework still be on the exam?
Yes, so the material on that homework, I think, is just more practice with least square regression lines, and those things are going to be on the exam, yes.
All right, thank you.
In fact, I would suggest still doing the homework before the exam because it's pretty great practice for stuff that you should know. Any other questions?
I'm sure this was already just said, but what day is the midterm again?
The midterm's Tuesday, so no class Monday. Midterm Tuesday.
Okay, thank you.
Any other questions?
Will we be using Excel on the exam?
Yes. You should, it's open notes and you should have access to Excel.
Okay.
I think
thanks.
technically, technically, I think you could use a calculator for everything that's actually on the exam, but I think it would be easier to use Excel, and it would be great practice since one of the goals of this course is to teach you how to use Excel. All right. So. Let's jump in. By the way, this is what my handwriting actually looks like, so I guess don't judge me too much, but least squares regression with a categorical variable. So this is sort of a tangential topic to what we've been doing. So this scatter plot shows a set of auction prices on eBay for the game Mario Kart. And I looked it up. It's the Mario Kart for the Wii. Has anyone played that one?
Best game ever on the Wii.
I love that game on the Wii. Don't even get me started. You could race ghosts of yourself and try to like beat your scores. Anyway, another tangent. We've recorded the auction prices, and we've also recorded the condition of the game. Which is either used or old. Or new, excuse me. All right, you can see, like these are scatter plots, right? Every single observation here is a single auction price and whether or not that price was a game that was used or new. And you can see, and indeed, we have that we can fit a least squared regression line to this data. So recall whenever we originally fit a least squared regression line, we had something that looks like this. Y equals B0 plus B1x. And implicit in our assumption is that x is a numeric variable. and that y is also a numeric variable. Right? But note here, x is no longer a numeric variable in this case. It's actually a categorical variable. It's either used or new. Right? So we have to use something called an indicator random variable to replace x. So we're going to replace this with an indicator. And I'm going to tell us what an indicator is right now. An indicator variable which here is cond new. And I'm gonna repost the photo so you can see it, but let me finish this definition first. Takes a value of 1 when a certain condition is met and a value of 0 otherwise. So let me post the photo again so we can see it. So we actually have our least square regression line right here. And you'll see this is our output, our y value, right? This is our y-intercept, b0. This right here is our slope, b1. And then we have this thing that they call cond new, and this is our indicator. Basically, the idea is cond new takes in two possible values, either used or old, or new, excuse me. Right? It can be one of these two options. And if it is used, we take a value of 0. If it is new, we take a value of 1. And I'm going to show you this with an example. So if this doesn't quite make sense to you, that is okay. Maybe it'll make sense with you when we actually use data. So if I had a new game, my best guess on its auction price would be, well, I want to make a prediction on price. And that is, according to my equation up here, is 42.87 plus 10.9 times the indicator random variable, or the indicator variable, let's just call it. And it's evaluated at new, since I have a new game, right? Okay. So whenever I plug in new to my indicator random variable, the whole thing just becomes 1. So this is just equal to 42 plus 10.9, which is $53.77 would be my best guess at the auction price of that game. And note, I can erase some of this stuff. Note, if I had a game that was new, right? My best guess is right here on the line. Sure enough, it looks like it's about 53 is the price. Okay? So that's kind of how it works. And the reason we do this is because we can't just plug in the word new for x, right? That doesn't make sense. What's 10 times the word new? We have to sort of encode it as a numeric so that when we kind of put things into our equation, we get a meaningful result from it. And that's what we're doing here. So similarly, if my game were old or used, excuse me, I keep saying old. I think it's because new. I think the opposite is old, not the opposite being used. My bad. Price is equal to 42.87 plus 10.9 times this indicator evaluated at used, which is equal to 42.87 plus 10.9. When it's at used, the whole thing just becomes 0, which is just 42.87. Okay, make sense? All right, so this is just, it's not too much of a theoretical jump based on what we've done already. The big new idea here is that we have this thing called an indicator random variable that allows our input to be a categorical variable. But note, this only works for categorical variables of 2 levels. It's one or the other, or a binary in our situation. All right?
So would we be given that equation, or would that be like part of finding the p-value on Excel, and then it would give us this like new
Okay,
part?
so yeah, so it wouldn't be a p-value. That's something different. But yeah, this situation are old equations. In fact, that's a good point to make. Here, the equations that we had, which are what? B0 equals, and B1 equals R times SY over SX, don't work. Okay? Actually, I'd have to think about it. If you plugged them in, no. If you used a categorical variable and you didn't encode it as a numeric, then no, they wouldn't work. So use Excel. And actually, that's what the video lecture is on. I walk you through how to do specifically this sort of situation and how to draw a trend line and get an equation using Excel. Okay, good question.
Thank you.
All right, so that is indicator random variable, or indicator variables. I keep saying random, they're not random, they're just an indicator variable. Indicator variables are something different that I use more often than this. Okay, let's look at the next thing. All right. When we fit a least square regression line, we generally require the following: linearity, which is data should follow a linear trend. 2, nearly normal residuals. Which we know that this isn't met. When we observe outliers or highly influential points. And I'm going to define influential in a second, so we're going to come back to that. 3, constant variability. Which means that the variability around the least square regression line remains roughly constant. And oh boy, I didn't write this in my notes. Let's see if I can do it. Okay. Heteroscedasticity. Oh crap. Okay. I don't know if I can spell this word. Skedasticity. That's totally not it. There's a K in there. Skedasticity. Maybe there's another I? Oh my goodness. Okay, look on the last notes and let me know how to spell this word at some point. But heteroscedasticity is something we don't want, and that's something that breaches this third point, which is then we see sort of like a fanning of our residuals on the residual plot. And actually, why don't I have an example to motivate these three. So these are our 3 ideas. Maybe I'll zoom out a little bit. And here, I believe, oh wait, no, not this one. Note these different regression lines. And note actually something kind of interesting. Even though all of the data are very different, the regression line themselves are all very the same. And actually, the only one that you really want to use regression on, the only one that really meets these 3 conditions, is this one. Yes, we see the data has a linear trend. The residuals, there are no main outliers or influential points. And there's this constant variability idea that there's sort of like a scattering above and below our line. So this one's good. This one is not good. And what we would call this is a non-linear trend. This one is also not good. There is a outlier / highly influential point. And this one, I believe I wanted to say maybe. And oh goodness, I'm running out of space. I need to zoom in. There's just one influential point. And all others so I say maybe because if we were to look at this just by itself, it would be a no. But think about our last case. What if these are actually 2 categorical variables? I just have it on a weird axis, right? Then maybe it would be okay because then we would just be doing the first thing that we talked about today right here. Right? So I would say set D requires further investigation. Set C and set D are definite no's, and set A is an A-OK. A-OK. Okay. So whenever we're thinking about regression data, whenever we're looking at scatter plots and we're trying to think, should we build a least square regression line, or maybe it's not that important here, there are 2 other ideas that we should think about, and I'm going to define them. And that is actually the last thing we have to cover technically before the first midterm. So the first thing we want to define is leverage. points that fall horizontally away from the center of the cloud. And I'm going to use cloud kind of with a cloud because I haven't precisely defined that. Tend to pull harder on the line. So we call them points with high leverage. And I have, hopefully, some examples of this. This is a picture you've seen before. All right. So there are a number of points here, and some of them have high leverage. I think one of them really doesn't. So the idea of leverage is that it is distinct and far away in the x direction. So only thinking about it horizontally. So in this case, thinking about this horizontally, these values are sort of between here and here, right? Don't think about their y values, think about just their x values. They're sort of between here and here, if this is the x-axis and this is the y-axis. This point, however, is way far away in terms of x, right? So we would say this point has high leverage. Same thing for here, actually. The points are spread out in an x direction from here to here, and this one is sort of off by itself right here. So this point also has high leverage. In fact, these as well do. Maybe not quite as high as these first two, but they're certainly off by themselves in the x direction. This one very much so. This one as well. It's sort of below all the rest of the values in the x direction. So this is something, I mean, a point having high leverage, I mean, it might mean something, it might not. It's just the terminology that we use whenever we see something along these lines. If it is away, like if the data are sort of in this cloud by themselves and there is one value that is way away in the x direction, we call it high leverage. Here, actually, this point doesn't really have high leverage. So I don't know, maybe I'll say low leverage. I mean, it may very much be an outlier, but it is not separated in the x direction. It's separated in the y direction, right? So we'd call some of these points influential, which I've been, all lecture today, I've been throwing around this word influential, so I'm finally going to define it. I'm sorry it took me until now. A point is influential if had we fit the least squared regression line without it, the influential point would have been unusually, and I'm spelling unusually wrong, just like how I spelled heteroscedasticity wrong, would have been unusually far from the least square regression line. So I'm going to post our photo again. So the idea here is influential points are points that sort of pull our line out. Oh, goodness. So I would call, let me see here, I would call this one a very influential point. And the reason that is if I were to get rid of it and draw a new line only with the data that were here, I would expect that line to look something more like this, right? So the fact that the presence of this point is considered, this point is considered highly influential because of its distance from the line that we would have drawn had we not included this point. So the fact that this distance is so great it implies high influence. Okay? So look at this point. It has a high leverage, but if we were to get rid of this point and draw the new line, frankly, I would expect the line to not even change at all, right? The trend was already very much in that direction, and getting rid of this point that's sort of off by itself doesn't have a lot of influence on how we draw our least square regression line. So we would call this one not very influential. Okay, and maybe we look at some of these other ones. This one looks somewhat influential. I would expect if I had gotten rid of it, the least square line I would have drawn probably would be more like that. So it does actually move it. So somewhat influential. This one also, maybe not as much. This one looks like, this regression line looks like it's going down there anyway. This one is somewhat influential. I bet the regression line would look more like that if we didn't have it, right? And these are also somewhat influential. The really influential one is this one right here. Okay? So the idea of influence is if you get rid of the point, how much does our least squared regression line change? I have a caution. It is tempting to want to just remove these points. They're kind of a nuisance. But I'm telling you now, don't do it. Models that ignore the exceptional cases often perform poorly. So the fact that these points are so much different than the rest of the trend, it's interesting, and it's kind of cumbersome if we want to build a least squared regression line, but ultimately it doesn't mean that it doesn't represent the truth. I mean, certainly if you investigated, for example, if we investigated this point and discovered it was only there because somebody messed up and put in the wrong value, right? That would be an example of something we could get rid of. But unless that happens, you got to stick with the data that you have. Don't just try to get rid of the stuff that's inconvenient. All right. So that is everything up through midterm 1, everyone. I have some other things to talk about, but are there any questions?
Yeah, I have a question.
All right.
Yeah, what makes influential points different from outliers?
Oh, that's an excellent
Or are they outliers?
Well, they're not mutually exclusive, certainly, but this is, I guess this is an example right here of a value that is probably an outlier, but it's non-influential. right? Because this value is certainly out by itself, and it's out there, and it's an extreme based on the data that we have observed. But it's not influential because it doesn't really affect, getting rid of it wouldn't really affect our least square regression line. Make sense?
Yeah, thank you.
Mhm.
So why might you remove outliers but keep influential points?
Well, I think what I'm trying to communicate is that you really shouldn't remove either unless you have a really good reason.
Okay, thank you.
Yeah, you only so when I was talking about removing these points, I mean, because to figure out whether or not they're influential, you remove them and you rescale the line. That doesn't mean you remove them permanently. It's just the calculation to determine whether or not they're influential is get rid of it and see if something changes. That doesn't mean like throw it away forever and then just keep the change. That means investigate the change.
Okay, thank you.
What's the difference between something that's like high leverage and then high influential? Like, aren't they similar? Or...
They're certainly similar, and they both talk about things that can affect our least squared regression line, but they're not the same. And I think the example of why they're not the same is actually this one right here. So this one is low leverage, right? It's not different in our x direction, in our horizontal direction. Leverage gets at how different is it in a horizontal direction. It's different than influence in that regard. So I would call this one like no leverage maybe, or low leverage. And then I would call this one somewhat influential. And the reason it's somewhat influential is because if I were to get rid of this point, I would actually see a change in my least square regression line. I would expect it to go kind of like that. Maybe not quite that dramatic, but yeah, it's not like hugely influential, but it's definitely pulling our line down, even though it's not different from these values in the x direction.
All right, thank you.
Yeah. Any other questions? Okay.
Oh, sorry, I have a question.
Okay.
The leverage part, because you said that like high leverage points are spread out across the X, and I think you used number 3 as an example. For one, could you use the like least squared regression box at the bottom to show it?
So I don't know if I meant to use this box to show it. I'm trying to think if that's, I don't actually know if that's always true. Maybe, as long as it's not a vertical line. So
I guess like what would be because that number 3 is an example of a high leverage.
Yeah, I would call this one high. It's not as high as this one, but there's certainly some separation in the x direction right here.
And it's not as high as 2 because 2 is closer to the line of best fit.
No, actually, this one 3 is higher than 2. So, excuse me, 2 is higher than 3. So leverage. Here, let me write it this way. 2 has more leverage than 3. And the reason that is, think about only the x values of all of these points. So let me zoom in. So this point right here has an x value here, right? Not thinking about the y values at all. This point has an x value here. This point right here has an x value, has this x value. This is my x-axis. And actually, all the points here, they look like they kind of scatter in this area. And then I have one x value all the way over here. So leverage is only getting at difference in x's. It's getting at horizontal difference. So the fact that this difference between everybody else and this one guy, the fact that this is so great, this distance right here, that's what gives you high leverage. It's specifically about large horizontal difference from the rest of the data. This one as well, it looks like the x values kind of range in this area. And then we have one person over here. And again, there's a distance between the horizontal grouping of this group and this value right here. But what I'm saying is this distance is not as significant as this. This distance is not as significant as this distance. So 2 has more leverage than 3.
Okay, compared to like 1, which is like on the vertical, it's like more vertical. It's
Yeah. So if you look at the first one, think about all of their x values. This has an x value right here. This is an x value right here. This one, this weird point right here, has an x value right here. They're all kind of scattered about here. This one's horizontal direction is not different. And so we wouldn't call this a high leverage point.
Okay, thank you.
Yes, of course. Any other questions?
So a point, I just want to double check something. So a point can be high leverage but not influential, and it can be low leverage but influential.
Yes.
Okay, thank you. I just wanted to double
They're
check.
just two different ways of thinking about data in the context of least square regression lines. Like if somebody
Okay.
put a least square regression line and show you a bunch of points, you could say, oh, this point has high leverage. Oh, this point seems like it's really influential. I'm trying to teach you the vernacular of thinking about least square regression.
Okay, thank you.
Any other questions?
If I had a question about the homework, can I ask that now?
So I have one more section to do, and then I'm going to field questions. So how about we hold that till the end of class? We will have time.
Okay,
Okay.
perfect.
Yeah. All right. So maybe I should go ahead to that next section. So this won't be on the test. It's just because I thought it was really interesting, and we had a bit of extra time. So recall our county data. This one. So if you recall, these are a bunch of different counties in the US and a bunch of different qualities of them. So we had like the state in which that county is, we had their population in 2010, the percent of the people in that county who are impoverished, things like this. I want to first define what I'm going to show you, and then I'm going to show it to you. An intensity map visualizes a numeric variable over a set of geographic locations. Colors are used to show higher and lower values of a variable. So rather than dive too much into this definition, let me just show you one. I believe, I always get these mixed up. This is the first one. So this is an example of an intensity map. This is poverty, percent poverty, I believe. Oh, no. Yeah, this is the other one, my bad. This one is percent home ownership. All right, so let's take a look at this. So it would appear that darker colors refer to a high percentage of home ownership. And the lighter colors is a lower percentage. So I don't know, let's take a look at it. I don't know, it would appear this section has not that many people who own their houses. Looks like there's a place in Arizona, a county in Arizona, where like everybody owns their houses. I wonder if there's just not that many people there. And the people who are there definitely own their homes. I don't know. What's somebody's hometown? Let's find out what your percent of home ownership is. Anyone? Should I look at the chat?
Fairfield, Connecticut.
Connecticut? Okay. Wow. So I can't spell and I don't know geography. Help me out. Is it here? Up, down?
It's more north.
Okay.
And like you see Long Island where it juts out.
Okay, this is Long
New
Island.
Jersey. Nope, it's a little bit above that.
So like,
Keep almost there. Keep going a little bit further up, and then to the right.
here.
A little bit more right.
All right, so you are here, right?
It's not the peninsula, but above that, like the
Here.
work. Yeah, there you go.
Very nice. It would appear, let's see if we can read this. It would appear in your area, there's like one section that has a pretty decent, maybe around like the 80% home ownership, but everybody else doesn't really own their home, or they have a lower percentage of home ownership. Pretty cool. So here, let's do another one. Why not? I think this one's more interesting. This one is, whoa, darn it. This one is percent of poverty by county. So dark means a high level of poverty. And light is a low level. Right? Let's look at this one. Looks like what the South moving into the mid-South has some levels of poverty. There's some juts here and here that might have them. I don't know. Anyone see anything that surprises them? So the idea of these plots is, besides the fact that I think they look really cool, I don't know about all of you, that they're a very good way to visualize how a variable is affected by location. So it is a quick on the top glance at how, in this case, percent poverty changes from county to county in the United States. That being said, this sort of plot is not a very good way, so great at looking at how geography affects a variable. But not so great at looking at that variable. So, so if I wanted to ask you, okay, so what proportion of counties in the United States have 13% poverty or lower? That is not something that you could very easily answer from this graph, right? First of all, you'd have to like count up every single county. And also this gradient, it's not very clear. Like, I don't really know this one right here. I don't really know if it's 13 or if it's not quite 13, right? So if you wanted to answer questions like that, you wouldn't go for a graph like this. But if you wanted to do exactly what we were doing, which is just kind of looking at regions in the United States and thinking about how poverty changes from region to region, these graphs are A-okay and pretty good for that, in fact. All right, any questions on these? No? I thought it was a fun thing to add. So this is the last, one of the last things. So numerical data across groups. So let's look at another data set, which is actually going to be a subset of this data we just looked at. So these data compare the median household. So the median household income for counties that had population growth between 2000 and 2010, and the median household income for counties that did not. So every single one of these values is a county, is a median household income in a different county, right? So this is a county, this is a county, this is a county. These are all their median household incomes. And they're split into two groups. The groups that had a population growth in that 10-year span and groups that did not. So we have two variables of interest here. We have a categorical variable, gain or no gain, and we have a numeric variable, which is median household income, all of these values. Got it? And I'm going to show you a way that we can visualize the relationship between these two variables. I'm going to show you two ways, actually. So these are two things. This one is called a side-by-side box plot. This one is called, I think this is such a dramatic name, but a hollow histogram. Maybe it's not dramatic, maybe like poetic. It reminds me of like an angsty person saying like, oh, I'm so hollow. All right, so this is a hollow histogram. And what it shows us is the distribution of each of these numeric variables split into these two groups. So all of these numeric values went into making this box plot, and all of these numeric values went into making this box plot. Make sense? And we can try to make a comparison between the two of them. What? If there was a population gain, it would appear that the median household income for places where there was a population gain is above the median household income for places where there wasn't any sort of gain. I don't know what sort of conclusions we want to draw from that. I don't know if we should draw any conclusions from that, but it is what our data is telling us in this plot. Similarly, this is actually two histograms of our data. So in this case, this one is going to the red. Oh wait, no, that's gain. My bad, wrong way around. This one is showing us the blue one, gain, and this one is showing us the red one, no gain. And actually, these are each histograms, so there should really be bars in the middle here. But you'll notice if you were to draw the bars and then overlay two histograms, I mean, already I'm drawing the bars on these, it's less clear, right? So what they do is they hollow it out. That's why it's called a hollow histogram, and you just see the outline of the histogram. And that way we can sort of compare the two distributions, right? It would appear, I would say just looking at these, it would appear that the center of no gain is sort of below the center of gain. And that was actually the case here as well with the side-by-side box plots. Okay, so just two new ways to represent a numeric variable where there is also a categorical variable that splits the numeric variable in half, like we have here. All right, any questions on these? Nope, right? So I am going to end my official lecture with an important lesson. Real data, maybe I should say real, are messy. I'm going to show us what I mean by that. On this one. So, can you all see my Excel screen? Yeah? I can actually only see a few of you. Yes, I got it. 1 thumbs up. There we go. So I actually went online to the Department of Health in the Philippines to get some of their data on COVID-19. And it would appear that their data is public and they release it every week. So this is the last week of COVID-19 data from the Philippines. And I looked at, there was a number of things. A lot of what they reported was different things going on in the hospitals, specifically how many COVID patients are in all their different hospitals and what sort of resources each of their hospitals have. And every single observation in this data frame is a different hospital in the Philippines. This column, beds ward O, is how many beds in their ward are filled or currently occupied by somebody with COVID-19. So some people have no COVID patients, some people have a few, some people have quite a handful. And the next variable is how many face shields, clean face shields, the hospital currently has in stock. So you'd imagine that we would hope that the hospitals with a lot of COVID patients also have a lot of face masks. But you can see from the data this wasn't really the case. It was the case for some of them, but it wasn't really the case for most of them. So most of our data are collected in this bottom left-hand corner, which means they either have no COVID patients or very few, but they also have very few face masks available, face shields available. We had a number on this right side over here, which showed something a little bit more precarious, where they have quite a number of COVID patients, but only a few or maybe even no face shields whatsoever. So in these cases, these are the hospitals that are in pretty wicked sorts, right? And then we have examples of excess, which is where, I call them excess, which is where we have huge amounts of face masks available to these hospitals, but relatively none or no COVID patients, relatively few or no COVID patients present in the hospital. So my idea of doing, I spent a while going through all of these different data sets last night. And in fact, I can show you if you'd like, give me 1 second. I used a lot, if any of you are into it, I used a bunch of R code to sift through things, and I'm gonna release this stuff on Sakai page because some of you mentioned you like using R. So if you're interested, I will post this. But after sifting through a bunch of the different data, I basically discovered what is unfortunately often the case is that things are really messy and a lot of the methods we've been learning don't really apply to this data. You would have to use something more sophisticated to get at any sort of interesting research questions about what we're observing here, which is like tons of scattering in this corner and then a ton of outliers. But nonetheless, you can still build a least squared regression line on it. And from this least squared regression line, I can build a residual plot. And as we've learned, this is a pretty terrible residual plot. I see a ton of spread on the left side, and then everything's kind of together on the right side. So heteroscedasticity, right? And doesn't really look linear. It's a bad residual plot. Don't do least squared regression. And know that in real life, data doesn't always really work out the way that you want it to. All right, so that was my COVID presentation, I believe. And also, I'm gonna keep sifting through because I think talking about the pandemic, especially considering the situation we're in, is a very interesting thing to do. And if you have any particular things you want me to investigate, shoot them my way. And if I have time, I certainly will. So that is all I have with regards to my lecture. What's going to happen next? I'm going to take, I think there was a homework question, so I'll take any questions you all have about content. And then after I do so, if you would like to leave, you're welcome to leave. I have a handful of practice problems that if you want to stick around, I can just work through them. If you want some extra practice, they are not practice problems that are on that practice problem sheet I released. They're just kind of bonus. And that's all I have for this lecture. So are there any questions, I guess, is the point of interest immediately.
I had a question on the
Yeah.
correlation where, because I looked on the forum because I was really struggling with it, and you said that you only needed like the slope and the y-intercept, and then when I like plugged it in, I'd only get like a correlation of 1, which was the case for 4, but for 5 I was struggling with it. So
Yeah. So
I just took the r squared.
So this was question 5, homework 6, I believe. Oh, wait, you might have just said it. You used the r squared.
Yeah. Is
Yeah.
that right?
No, that is right. So
Oh, okay.
it gave you r squared. So just do r equals the square root of r squared. Yeah? But a little warning about this actually is that whenever you take the square root, so the square root of r squared is actually equal to plus or minus r, right? So you need to look at your data, and if you see an upward trend, choose an r, make r positive. And if you see a downward trend, make r negative. Okay?
Yeah, thank you.
Did you just post the questions, the practice questions in resources?
Yeah, it's on the resources tab on Sakai. Let me know if you can't find it, and I'll post.
Is it midterm 1 preparation?
Yeah, that's it. That's it.
Okay.
And I'll post the solutions on Sunday. I'm gonna have a fun little me time on Saturday writing up answers. It's probably gonna involve a lot of tea. Speaking of which, any other questions?
I have a question about 4. Oh, you can go ahead.
I have a question on the same question, so.
Oh, so this was homework 6, question 4, right? Okay. What was the question?
I didn't know, why was the correlation like 1 if
Yeah.
like it was like more than or less than the woman and men question?
Yeah, that's because the different parts described a linear relationship. So I'm gonna make a guess. Say women. I know this isn't the case, but for my example, make 25% more than men. So the suggestion here, like this is, if I were to write this as an equation, it would be, so let men be y, women be x. It would be men make, wait, I'm gonna do this the other way around, my bad. So if women make 25% more than men, that means if I knew what men was, 1.25 times the value that a man makes is equal to the value a woman makes. And this is actually a linear relationship. So if I took some values for x, so say some men made $1,000, $2,000, and $3,000, right? So 1,000 would be, the y values would be 1,250, right? With 2,000, it would be double that, right? No, I should just do it this way. It's so like me to make these mistakes. Yeah, 2,500, and then this would be 3,750, right? So if based on this relationship described here, if men had these 3 values, women would have these 3 values. Do you agree with me up until now? Okay. Well, actually draw this. 1,000, 2,000, 3,000, 1,000, 2,000, 3,000, 4,000. Okay. So 1,000 like that, 2,000 like that, 3,000 like that. You'll note that if you just try drawing some points, these are all in a straight line. This part A, it describes a strictly linear relationship. And when points fit a straight line like this, they have an r equal to 1. It's possible they could have also defined, and I don't think they did for that homework. Someone could correct me if I'm wrong. They could have also defined a relationship that was completely negative, right? In which case the r would be -1. But r is only something with a magnitude in between -1 to 1 when you have points that are like nonlinear, but they're sort of in a linear trend, right? Which we don't have here. The kicker, and the thing, it's a difficult problem. A lot of people had some trouble with it. The kicker here is that they defined 3 relationships that were strictly linear. And if you just sort of guessed some points and tried drawing them, it would have shown that like it's a straight line, so it's going to be either 1 or -1. Okay? Did that answer both the questions, or was there something else?
No, that was also my question. Thank you.
Oh, cool.
You said that there could be like a -1 if it was like decreasing. For part C of that question, it was like 15% less than women is what men make. So I thought that would have been -1, but then it was 1.
So it's men make 15% less than women, right?
Yeah, because I know you could also just say women make 15% more than men. So I was like,
Yeah, so I guess the way to think about this is if a woman's value, as women's values increase, do men's also increase or do they decrease? So I guess you can do it the same way. Let's try it. So men make 15% less than women. So let's let women be the X value here and men be the Y value. So women make 1,000, 2,000, 3,000. What would men make? 1,000 minus 15%. So what is that? 0.85 times 1,000. Just 850. And then 1700, and then 2550. Okay, let's try to draw this. So x is 1,000, y is something a little bit below 1,000, x is 1,700, y is 2,000. No, I messed it up. X is 2,000, y is 1,700. Then x is 3,000, y is 255. Yeah, so it's still a positive direction. It's still a positive relationship. And
okay,
and the reason that is because if a woman's salary increases, a man's salary still increases. It just doesn't increase as much. So it's still they're both increasing, rather than if we said like women's increase, men's decrease, that would be a negative relationship.
Okay, and then when you were doing question 6, was that for part E about, I'm pretty sure, about the correlation coefficient?
Yeah, I assume. There's a part that asks for correlation, and the only thing they gave you actually was r squared. So you just square root r squared.
But I don't know if I'm like just missing something, but if it's 64 and the square root's like 8 point something, isn't that like way higher than it should be?
Yeah, so that's a great question. So this is question 6, homework 6, right? R squared is,
or actually question 5.
Sorry. R squared is given in percent, right? Convert it to decimal.
Oh.
Yeah, because you remember percent is the same thing as like point that, right? And the reason is because for the point you're actually making, it's way too high as a percentage. We need it as a proportion, and then we would square root the proportion.
Thank you.
It was like 6, 7. Something along those lines. Okay. Anyone else?
Yeah, could you review how to read the regression output in question 5? That was just a little confusing for me
Oh,
in writing out
yes.
the linear
And in fact,
model.
I think I posted this on Sakai because I worry that this was a little, I might have been throwing you in the deep end a little bit with this one, and I apologize for that. But
It's okay.
the idea is, I think it was like, and correct me if I'm wrong, it was intercept and then like body weight or something like that.
Yeah, that's what it was.
And then it
And
said
then across the
estimate,
top. Yeah.
T-value, and then this sort of like
And there was
probability.
standard error too.
Oh, standard error was here too. All right.
Mm-hmm.
So everything from here down, ignore. These values right here have to do with like certainty of how certain we are that we have the correct slope and intercept for the true linear model. And these are concepts that if we have time, I'm definitely going to come back to. But definitely for where we are right now, the only thing we care about is the estimate. And the thing right here is B0, and the thing right here is B1. So
Okay, thank you so much.
yeah, learning about t-values and learning about here, we need to first know about something called hypothesis testing, which is going to be a huge section in the next few chapters. So more to come. I really do hope we get back to this table and learn everything in it. But for now, the only thing we need to worry about are these two things. That's a good question. Thank you for bringing that up.
Okay, thank you.
Any other questions? Okay, so if there are no other questions, I have some practice problems. Come and go as you please. If you're interested in just going through some fun little problems with me, by all means, stick around. If not, peace, there's a lecture video. Take a look. It's a shorter lecture video. Let's start with this one. All right, so it's another portfolio one, which I believe showed up on the homework. Capital asset pricing model is a financial model that assumes returns on a portfolio are normally distributed. So we have a normal distribution. Something along the lines of this. Has to be perfect, right? Yeah, never mind, I give up. So it is a normal distribution centered at 14.7. So I think that's like right here. With a standard deviation of 33%. So think about the inflection points. That means this is right here is going to be 1 standard deviation above, which 47.7. And then 14.7 minus 33 is, I think it's 18.7. Negative 18.7, but you all should check me on that. So this is the general picture of our normal distribution. And what are we being asked? What percent of years does this portfolio lose money, i.e. have a return less than 0? So think about 0. Oh, goodness. Think about 0 right here, right? 0%. And we want to know the proportion of values at or below 0%. And as a quality of density curves, that is precisely equal to the area under the curve at or below this point. So this was step 1. Draw a picture. Step 2 is calculate a z-score. So z equals x here is, or I'll write the equation, x minus mu over sigma, which is equal to 0 minus mu, which is our center, 14.7, over sigma, which is our spread, 33. And this is, Let's see, 14.7 divided by 33 is negative 0.445455. Cool. So that's a z-score. And step 3. Is to plug that z-score into Excel. I will also do. This uses the norm.s.dist function at negative 0.445455, 1. And let me grab my Excel. Norm.s.dist. Negative 0.445455, 1. And it looks like it is equal to 0.3277995. Okay, or 32.7995%. So that is the proportion beneath this, right? Which is the percent of years that the portfolio loses money. Right? So this one should be pretty straightforward. Any questions on this one? Okay. All right, then I'll do part B. So we want to know, what is the cutoff for the highest 15% of annual returns with this portfolio? So again, I'll draw my normal curve. It is centered at 14.7. And I want to know the point. I want to know the point here such that it's going to be around here, such that the area above it is equal to 0.15. Right? So something to note about the normal curve is that if the area above the cutoff is 0.15, then the area below the cutoff is going to be 1 minus 0.15 or 0.85, since the total area of a density curve is always 1. So this was step 1. We drew a picture. For these sorts of problems, the second step is to use Excel to find the z-score. So on this curve, I wanted to know the x value such that this happened. But there's going to be a corresponding z value such that the area beneath it is also the area beneath that z-score is also 0.85. And if I find that z-score, I can then convert it into the x value using our unstandardizing formula. But first, let's find that z-score. And that is actually just going to be done using the norm.s.inverse function evaluated at 0.85. Now, note I used the lower probability rather than 0.15 because Excel always assumes you're using the lower probability, which is kind of why we have to flip our thinking once in a while. So if I plug this in, let's see what it is. Norm.s.inverse of 0.85. The z-score here is 1.036433. And the unstandardizing formula is x equals sigma z plus mu. And I know sigma, it's 33, right? It was given to me in the problem statement. The z we just found using our norm.s.inverse function. And then I can add on the center, which was, it was 14.7, I believe. Let's do this. So 33 times u plus 14.7 is 48.9023% of portfolio percent return from portfolio. Okay, so that's how you do this problem. Any questions, or should I'm just gonna keep doing practice problems. Are we good? Yeah.
So when you plug it like the norm.s.inverse 80.85, that gets you the z-score of the bottom half, or the bottom.
It gives us the z.
The bottom.
Yeah, it gives us the z-score such that the area at and below the z-score is 0.85.
Okay.
And the norm.s.inverse function always gives you the z-score such that the area below your input is that value. So I put in 8.5, it would give me the area, the z-score such that it has an area below equal to 8.5. If I had put in 0.15, so if I had put 0.15 in here, it would have actually given me a z-score down here. Right, because this z-score has an area at or below it of 0.15.
Yeah.
Right.
Okay.
That's why we had to do the backwards thinking kind of thing.
Yeah. So if the question were to ask like the lowest 15, then you wouldn't have to.
Yeah. In that case you would put 15.
The other math. Okay. Okay.
Exactly. No, it's a great point. Any other questions? Okie doke. Another practice problem. Let's do this one. So a survey was conducted on 218 undergraduates from Duke University. Oh goodness, I didn't realize this was from Duke. Maybe I should just, excuse me. Okay, who took an introductory statistics course in spring 2012. Among many other questions, the survey asked about their GPA and the number of hours they spent studying per week. The scatter plot displays the relationship between these two variables. So we have study hours per week, GPA, and then each of these are different students who reported, right? What is the explanatory and the response? So by convention, the explanatory is always on the x-axis, so it is study hours per week. And then always by convention, the response is on the y-axis, which is GPA. So describe the relationship between the two variables. Make sure to discuss any unusual observations, if any. So, so I would say, just looking at this data myself, I would say either weak positive association, or maybe even no association. They seem pretty well scattered. And if there is an association, it's not that strong, right? I might be able to draw kind of a linear trend like this, but it'd be tough, right? I'd be kind of hand wavy about it. As far as unusual values, I would kind of point to this. I don't think there are AP classes in college, so I'm pretty sure you can't get above a 4.0. I don't know. Duke's pretty extra, maybe. I actually didn't even go here for undergrad, so the animosity of Duke is something I get from my father, who went here for undergrad. And to this day, he just turned 60, and to this day, he complains about Duke, which I think is so funny. So yeah, that's a weird observation. This one also, it looks like somebody is working like 70 hours per week, which is insane. I guess they don't sleep. Maybe them not sleeping is the reason they don't have a 4.0. Or maybe they're just really hardworking. I don't know. So yeah, this is the sort of analysis you would do for something like this, I guess. C, which is this an experimental or observation? Easy. This is an observational study. There's no treatment that we applied. And then D, can we conclude that studying longer hours leads to a higher GPA? The answer is no. causation cannot be inferred by an observational study. So even if we did find a very good positive relationship between two of them, we couldn't really say one causes the other unless we did an experimental study where we sort of control for confounding variables. There may be a confounding variable that's actually causing the changes in these and not necessarily each other. Okay, any questions on this? All right, I have one more and then that's all I got. And this one shouldn't be too long. I didn't actually even do this in the last class. Oh, ooh, this one's kind of nasty. It makes me feel weird. So workers at a particular mining site receive an average of 35 days off paid vacation, which is lower than the national average. The manager of this plant is under pressure from a local union to increase the amount of paid time off. However, he does not want to give more days off to workers because that would be costly. He instead decides he should just fire 10 employees in such a way as to raise the average number of days off that are reported by his employees. In order to achieve this goal, should he fire employees who have the most number of days off, least numbers of days off, or those who have about an average number of days off? So recall our average calculation. This is sample average. Is the 1 over the number of observations times the sum of our values, okay? Or we call this X bar. So we want to know how to make X bar increase by getting rid of observations. So I'm going to tell you, you should get rid of the people at the low end, but hopefully I can kind of argue that to you visually. Think of a number line. So this is, the average is 35, so we'll put 35 here, and maybe 30. So what is this? 30, 25, 20, 15. And X bar is right here. So what if the points here correspond to different workers, and it looks something like this? I think he said, how many? Oh, he wants to get rid of 10. So I'm not getting rid of 10. I don't want to draw that many points. But the question is, which point should I get rid of to move X bar that way? And you can think about each of these points are sort of pulling X bar towards them. That's kind of how this calculation works. So that being said, if I get rid of some points down here, these are no longer pulling X bar downward. Hence, X bar will increase. So if I want my average days off to go up, I should get rid of the people who have a very low number of days off that they take, and then the average will increase. Does this make sense? I guess it's a little hand wavy, but that's kind of how the mean works. Okay. This was my last practice problem. So if there are any questions, I'll take them, and if not, that's it. Happy studying this weekend.
Thank you.
Thank you.
Thanks so much.
Thank you.